So looking at the pink form, we are given a function. Obviously, it's polynomial. What is its degree?
All three.
6.
So one more time. So this is degree 3. This is degree 2. This is degree 1. Degree 3 times degree 1 times degree 2 is
6.
right. Are we okay with that? Yes? Okay, perfect. So then I start my table right away. So I copy it here so I don't have to go back to that. So I know it's degree 6. I know it's going to have 6 solutions. X equals 0 3 times, multiplicity 3. X equals negative 3 multiplicity 1, and x equals 1 multiplicity 2. So 3 plus 1 plus 2 must be 6, and it is. Then we know that polynomial functions are friendly. We never have to worry about them, meaning I don't have to think about the domain. I like friendly functions. So we have negative 3, and we have 0, and we have 1. Multiplicity 3 is a cross, but slow. Slow cross. Multiplicity 1 is just a simple cross, but multiplicity 2 is a turn. This is degree 6, which is even. It has this end behavior or this end behavior. Behaves like x squared or like negative x squared. Because the leading coefficient is positive, it will be positive infinity to positive infinity. There is no point in talking about the y-intercept because I already have it. There is no point in talking about symmetry, but I will write it. F of negative x does not equal f of x and does not equal negative f of x, not symmetric. And there is nothing else I need. So this is like a half a minute problem. And I want you to treat it like that. I don't want you to waste too much time on it. So we have negative 3, we have 0, and we have 1. It's coming from positive infinity, and it crosses straight at negative 3. But it has to turn because it has to cross again, a slow cross at 0, 0. So it turns and crosses slowly at 0, 0. It has to come to a maximum because it comes back and turns again at 1. So it has to have a maximum, turning again at 1, and going to infinity. And this is our f of x. That's it. That's what I want you to do. Just half a minute problem. That's all you need, right? So you look at the function, identify its degree. The maximum possible number of turns is 5. Max turns 5. It does not turn 5 times. It turns twice. It turns 3 times. 1, 2, 3. So it doesn't have to turn 5 times. But that's it. You are determining the x-intercepts, their multiplicities, and the graph is there. You don't need the calculator other than finding the max min, because in this class we can't. Once you take the next class, you're going to see you don't need a calculator to find max min. So in y equals, we put it next to the third, and then parentheses, x plus 3. It takes longer to punch it in the graphing calculator and find the max and the min than graphing it. And x minus 1, right? So x minus 1 squared. So I don't really want to use the standard, but for now, let's see. I'm going to use the standard and see what happens. Okay, so I know it's lying. The graph cannot be on the x-axis. It has to have a minimum. We know that because it crosses slowly, right? And it has a maximum and then turns again. But you see here, if you copy that, then I know you have no idea about this function, right? So please don't copy anything without thinking. So obviously this is a mess. So I have to adjust the viewing window a lot. So first of all, -3 is good enough. X maximum +3 is good enough. And Y minimum, well, it has to be huge. I have no idea how big. I'm going to say -50 or -60. I don't know what you found. So, and Y maximum, 2 will be more than enough. So let's see what happens now. Still not enough. That minimum is beyond -60. So I go back. I'm going to say this time -100. I'm focusing on the minimum for a second with a scale of 20. Now let's see what happens. Finally, I can see this. So it's obviously between -3 and 0. So I'm going to find this minimum with second and calc. Minimum, which is a 3, between -3 and 0. And I don't want to guess. Just give me the minimum. So the minimum is at -2.45. -2.45, and the minimum value is -96.3. Now I'm going to forget about that. I don't care about it anymore. I care about this piece now, right here, between 0 and 2. So I go to the viewing window between 0 and 2, and now I want between -2 and 2 with a scale of 1. Just show me that piece. Exactly as I expected. So it's crossing slowly. It goes to a maximum. It turns at 1 and goes to infinity. And I want to determine this maximum between 0 and 1. So, bless you. Second and calc. No, that's not second and calc. This is second and calc. So I want the maximum this time. Left bound is 0. Right bound is 1. And I get at 0.61, comma, 0.12. It's a big maximum, 0.12. So it took us much longer to punch in the graphing calculator. Of course, I pressed the doc cam for like the other class. Sorry about that. So it took us longer to punch it in. It's more difficult with a computer than with a calculator. It took me longer to punch it in and find the max and the min and the max than graph the function. You can also put it here as -2.45, -96.3, and 0.61, 0.12. Yes, David, go ahead.
When I put in my window the same points that you did, like for the Y min and max, it's pretty much every given error.
I have to look at it. I'll be more than happy to. If you have a minute at the end of the class, I'd like to look at it and see what happened.
Work for the X.
I'm sorry?
When I try to find the maximum, to work for the maximum. When I was trying to do it.
Yeah, so if the minimum is not in the viewing window, it will not give you the minimum.
Okay.
So you have to make sure, that's why I keep adjusting the viewing window, so if the minimum shows, then it will give me the minimum. If the minimum does not show or the maximum does not show in the viewing window of the calculator, I think it's not going to give you anything or an error.
It depends,
It does?
it depends on the type of calculator.
It depends on the type of the calculator.
The 84 plus shows it.
Okay. Good. So let's look at the other one. Any questions on this one? Any questions? Is it clear now? Yes? Okay. So let's look at the other one. The other one was a rational function, which is f of x, x over x squared minus 4x. Obviously, I did not look at what you did. Just what, and not all of them, right? So I just took your papers and I maybe just glanced over the paper. And I think I only saw one student who did this correctly. But I could be wrong, and I apologize if I am. So, first of all, we factor the denominator. We state two restrictions. And we simplify to get 1 over x minus 4, which means that this is a whole and this will be a VA. So I was expecting everyone to do that in a blink. So negative infinity, 0, 4, infinity, undefined, undefined, whole, x equals 4, VA. Infinity infinities, and I did not check the sign yet. So every time we're given a rational function, we have to find its domain, like any function. We have to find its domain, and I can't find its domain if I don't factor the denominator. Once I factor the denominator, I see that something simplifies, and it makes it very easy. This is type 2. Horizontal asymptote is 0. I have to find the signs here with 3.9 and 4.1. With 3.9 is negative, with 4.1 is positive. I plug in 0, I get negative 1/4, and it's all done. There is nothing else. So I draw the vertical asymptote at 4, x equals 4. I draw the horizontal asymptote where there's no need. I plot 0, negative 1/4, which is kind of difficult, but it's somewhere here. From 0 through the whole at negative infinity. From positive infinity to 0. So this is f of x equals x over x squared minus 4x. There is no way you will not know how to do this if you do the problems we do in class. I refuse to believe that you're not able to do it. I refuse. Everyone can do this. Yes?
So we don't need x-intercept or y-intercept in this?
Well, can you plug in 0?
Yeah.
Can you plug in 0?
No, we can't do this, but
Can you find the x-intercept? It's 1 over x minus 4. When is a fraction 0?
when we talk from 0.
But the top is 1. So this function has no x and y intercepts. The top is 1. Can you make 1 into 0?
But,
There is no x in it.
but it's our normal procedure to do this, right? To solve the problem.
Of course, but there is nothing you can do. It's 1 over x minus 4. I just fill up my chart with what I needed and what exists, because if it exists and I didn't put it in, that's a problem. But it doesn't exist. So when x is 0, y is negative 1/4. So it's this hole in the graph. Okay, so the test is it's Tuesday, so I'm really begging you to redo the problems we did in class, all of them, so you are prepared for this test. It's not going to be anything other than what you saw in class. But if you don't diligently go back, then you're going to miss out here and there. Will you still get a good grade? Of course, it's possible. And I'll be more than happy to help everyone. But if you want to have a solid foundation of this, you need to work on the problems we do in class first, and then homework. Okay, so anything else you would like to go back to? Anything? Any questions? Any questions? Okay, so let's go back to chapter 6. Chapter 6 is not on this test, of course. Chapter 6 is going to be on test 3. There was one problem that last time, I think it was the last problem we looked at. Let me go back for a second to our previous lecture. I don't remember exactly which problem that was. After we started chapter 6, we looked at a word problem that has another possibility of solving it, which was this one, 63 on page 478. And I like to explore the other possibility. So 478. 63. Yes. So let's go back to that problem because there is another avenue that I would like, as I said, to explore. in this particular problem, in my opinion, but that's my opinion, and if I put something like this on the next test, you will be given the formula. I think the formula should have been given here. It's not. You will be given, even if the problem, you have copy a problem from here and it has no formula, I will give you the formula. Okay? Because I think it should be there. So, again we have, so let's go back to it. So 63 on page 478. So again we have, in 1985, they say the cost or the value was this. In 2005, they say the value was 145,000. And what was the annual growth rate between 1985 and 2005? Assume that the value continued to grow by the same percentage. What was the value of the house then in 2010? So we established something here. And what we established was that we were given 2 points. 1 point for x, for 1985 we said x was 0, and then for 2005 we said that x was very good. So we were given 2 ordered pairs. So then it was 20, you gave that to me last time, and 0, 110,000. So the formula that, in my opinion, it should have been given to us is given on page 471 as y equals a, the original value, b raised to x. So y equals a times b raised to x, where this is the growth rate. You're not going to be asked to guess this. This will be given to you. So then, using this formula, we're going to, because we have 2 ordered pairs, we will be able to determine the original value, the initial value, and the growth rate, x being the time, right? So let's write 2 equations. Can anyone give us the first equation for this? When x is 0, y is 110,000. So 110,000 equals a times b raised to 0. Can anyone give us a second equation with a second point? Yes, please.
145,000
Excellent.
is equal to a times b to the 20.
Excellent. So we're going to solve these 2 equations and get a and b. Obviously, b to 0, b is a growth rate, so it cannot be 0. Remember, 0 raised to 0 is not 1. Anything else, maybe I shouldn't use a to confuse you. Let me say t. Any number raised to 0 is 1 except when t is 0. T cannot be 0. So what is going on with the 0 raised to 0? You have to wait till Calc 1. And this is called an indeterminate case, not an undefined case. Indeterminate case. There are a total of 7. There are 7 indeterminate cases, and this is one of them. So obviously, b is not 0, so it's a number. Raised to 0 is 1. So of course, this was kind of redundant. We already knew that the initial value of the home, which is a in the formula, is 110,000. We knew this. So now we're going to put 110,000 in the second formula, in the second equation. So we have 145,000 equals 110,000 times b raised to 20. And from this, we will be able to determine the growth rate. What should we do first? What would you recommend we do first?
Divide 110 by 4.
Yes, of course. So I'm going to remove 3 zeros from here and 3 zeros from here. We should not do anything else. There is no need. Just write 145 over 110. And now what should I do to both sides in order to determine b?
Doing 1 by 20 do.
Yes, awesome, great job. The 20th root from both sides. And the final simplified form will be b equals the 20th root of 145 over 110. So with a graphing calculator, let's do this. So in parentheses, but that's me. You may want to find some, you use a different method, that's fine too. Power, what power would that be if you want to use power like I would? 1 over? Very good, awesome. Close the parenthesis, don't forget. And we get that the growth rate is 1.0139. We normally, for growth rate, you'll see later in this chapter, we prefer four digits. So 1.0139. Okay. So we're going to go back and put it in the formula. So the formula is y equals 110,000 times 1.0139 raised to x. If you want to call this, which I would, f of x, that's even better. So we established a model that fits the given information. Now they also want us to determine, assuming the trend continues, what will be the value of the home in 2010. So what do we need to do?
X equal 25.
Excellent. So we have f of 25. See, in this situation, I prefer the notation f of x because it's very clear to plug in 25 and then determine that. So with the calculator, I will put 110,000 multiplied by, in parentheses, 1.0. I'm going to recall the previous answer. And put the power 25, of course. Okay, so let's see what we get. 155,368, and when it comes to money, we'll have 2 digits after the decimal point. So 155.368, 368.09. That's it. Any questions? Any questions? Yes, please.
You put in 25, you asked me to.
It was 2010. So yes, it's 25 years from 1985. Okay. Let's look at one more, 65, and then we'll continue. So let's read 65. Again, there is no formula here. The formula will be given to you. So we have Jamal who wants to save $54,000 for a down payment on a home. How much will he need to invest in an account with 8.2% annual principal, annual APR, annual
Price for
not sure. So so there is the actual rate, and the APR contains all the fees. You can think of it right now. So compounding daily in order to reach his goal in 5 years. Okay. So let me look at the formula. Put the formula for you up here. Oh, sorry.
So annual percentage rate.
Annual percentage rate. Thank you. Yes, that's the yes. It's the one that includes all their fees and stuff. Okay. So here it is. We discussed this formula, but you don't have to memorize it. So let me tell you again what each and every one of them represents, and then we'll identify what is given. Very good. So this is what we want, the accumulated value, or what we have to pay if we take a loan. This is the principal. This is the number of years. time in years. This is the number of times the interest is compounded per year. Number of times interest is compounded per year. R is the interest rate. In this case, the APR. Annual percentage rate. Of course, it has to be a percentage. Okay, so now we know that he wants to save $54,000. Where does $54,000 fit in this formula? Okay, one more time, let's read. I think it's not clear. Let's read it one more time. He wants to save $54,000 for a down payment on a home. How much will he need to invest in an account paying this compounded daily in order to reach his goal in 5 years? Yes, Mike?
You solve it by first figuring out what you convert the percent to dollars, or like how much interest there is.
So just 1 second, let's identify what is given in the problem. Hold your thought. Yes, Haley?
We plug in 64,000 per annum.
For?
For N.
Okay, so let's identify. It's not clear. It's me. So this is the amount we deposit if we want to get that.
So the A is the 54,000.
Correct. This is the amount we borrow, and this is what we end up paying at the end of the loan. So this is what we want. This is the amount we need at the end of the 5 years to put down on a loan. So the accumulated value is indeed 54,000. This is our target. We want to deposit blah, but we want 5 years from now to get 54,000 out of it. Is this clear for everyone? Yes, perfect. Now, what is the principal?
We have to find this.
We have to find the principal. Excellent. Good. 1 is 1 plus. What is the interest rate? The interest rate is 8.2%, but it has to be 0.082. So 0.08, is that what you meant, Mike?
Yeah.
Changing? Yes, perfect. Now, what is N? We're told that the interest on this loan, or deposit in this case, it's a deposit, is calculated or compounded daily. We normally consider that a year, although, as we know, there are leap years and so on and so forth. So we normally consider a year to have, so it has 365 days, therefore it will be compounded daily. So now N is 365, and now T is 5 years. So we identified in the formula each and every piece of information that was given. We realized that we don't know how much we deposit to get this amount 5 years from today. Is that clear now? Okay?
Is it a word problem here?
Yes.
So he's saving up to put a down payment of 54,000 down on the
So
home, right?
he needs 5 years from today, he needs $54,000 to go and put down a payment on his house. This is what he needs in 5 years from today.
Okay.
So he wants to save this. He doesn't have it. He wants to save this for a down payment, blah, blah, blah. How much will he need to invest today in an account that pays 8.2%
When he wish will give him 54,000 in 5 years.
in 5 years? So he doesn't know how much he should deposit at a bank that pays this. So then 5 years later, he will go in and take everything out and go to a mortgage officer and give him the money for a house. Better?
Yeah, I was thinking that it was maybe ballpark.
Right. So word problems, that's a very good example. Word problems need to be read more than once. Right. And I encourage you to do that. Excellent. Thank you for your question. Okay, so then, here's what I recommend in one step. Yes, you can deal with that. Oh, yes, sorry. Thank you. Thank you. Thank you. What I would do, I would just write this in one step. One calculation, 365 times 5. However, doing it piece by piece will introduce a lot of error. That's why we want one calculation at once. So now, we're going to put the whole thing in the graphing calculator. Because the numerator is just one number. There is no need of parentheses around the numerator. But there is an absolute need of parentheses around the denominator. In addition to what you see. So once you put it in the calculator, you need this. You do not need this for this situation. So 54,000 divided by, in parentheses again, a 1 plus 0.082. Your calculators may be sophisticated enough to do this. I don't know. I have to look at it. Caret, parentheses, 365. But this is what I recommend, times 5. Close the parenthesis, come down from there, from the numerator, from the power, I meant to say, and put another parenthesis. So in order for him to get 54,000 5 years from now, he must deposit today 35,838.76. That's the principal. 35,858.76. But be very careful how you put it in. Did anyone else get the same answer? Yes? Excellent. So very carefully put this in because parentheses are crucial. The calculator will do something else, totally. We looked at the graphs of exponential functions, and I would like to remind you of those graphs and then look at some problems. So we are still in 6.2, exponential function. There are two different situations. Like two different situations for quadratic functions. 1, 2. Like two different situations with cubic functions. 1, 2. Same thing here. One of them is when the base is greater than 1 and the function is increasing. So this is f of x equals a to the x, where a is a greater number than 1. You may not know, but you can run them over. Sarmad, you can run them over with a truck. They will not break. I'm not kidding. Okay, so the other one is this situation. Still f of x equals a to the x, but this time a is a tiny positive number. We analyzed this last week. Whenever the base is greater than 1, the exponential function is increasing on all its domains. When the base is less than 1, between 0 and 1, the exponential function is decreasing on all its domains. They are both shapes, and the function, of course, is 1 to 1. Therefore, without even knowing anything about its inverse, we can graph it by simply reversing the coordinates. And we will get this, which is the f inverse for this function. And we will get careful, please remember that. We will get this inverse for this function. So this is what we looked at so far. We have not gotten the chance to look at transformations with this function, of course. You can't get away with transformations. So now we are adding these two functions to that long list of base functions. We had linear, we had quadratic, we had cubic, we had rational, we had fourth degree, we had absolute value, we had square root, we had the cube root. Now we're adding these two, the exponential function and its inverse. But for now, let's look at the exponential function. And I would like us to work on some transformations. Please choose whatever you like from here. And use transformations. What about 30? 30? Yes? No? Yes, very good. So 30. On page 489, we're asked to graph using transformations. F of x equals 3, 1/2 to the x, and minus 2. Let me see how I'm doing on time with this. Oh, that's fine. Okay. Can anyone identify the base function? So let me write this down for you. Graph using transformations. Base function, please. Yes, please, baby.
So 1/2 x.
Of course. It's the base function is the exponential function with a base 1/2. Absolutely. Good. The first transformation on 1/2 raised to the x.
Minus 2.
Never. In order of operations, I cannot jump to that.
Multiply by 3.
Multiply by 3. Very good. So in order of operations, 3, 1/2 to the x. What does that do to the base function? Vertical stretching by a factor of
3.
very good. Vertical stretching by a factor of 3. Good. Now, obviously, 3, 1/2 to x minus 2. What does this do? 2 number 1. Yes, absolutely. Perfect. So down 2. Perfect. Now, when I graph 1/2 to the x, do I graph it like this, increasing on all its domain? Or do I graph it like this, decreasing on all its domain? Decreasing, because the base is less than 1. When the base is less than 1, the function is decreasing. Now, since the function looks like this, if I want to shift it left and right, does its horizontal asymptote change? No. But what if I want to break it down or up? The horizontal asymptote moves with the graph. If I shift it up 3, the horizontal asymptote moves up 3. If I shift it down 4, the horizontal asymptote moves down 4 with the graph. So please keep that in mind. Perfect. So let's graph. So this is the base function, 1/2 to the x. Then you told me to stretch it by a factor of 3. That's kind of hard, but I know that this is 1, so it's going to go to 3. And all these heights also get multiplied by 3. So now this is the new graph. So maybe it should be a little higher. So this is 3 times 1/2 to the x. But now I have to be careful because you said correctly, move it down 2. But I have to shift the horizontal asymptote first. Where do I shift it to? Yes, y equals -2. This point moves down to right here. This point moves down to, I'm not sure where. So this is the graph of a 3, 1/2 to the x minus 2. As you see, the original graph did not have an x-intercept, but this one does because it shifted down by 2. Any questions? Please.
If we were to do this assignment with paper quiz, would you like us to show all three graphs, or would you like the final step?
It's a very good question, and that helps with the test. And thank you for asking. If you present each transformation what it means, I'm fine if you just graph the last function. But if you don't present what it means, each and every one of them, then I want to see each graph in the correct order. If you want to put all of them on the same coordinate system, I'm fine, as long as I can read it. If you want to put them on separate, it's fine too. It's up to you. But just show me that you know what transformations are and how you apply them in order of operations. And if you just graph the last function, it's fine, as long as you may be asked to find the x and y intercepts algebraically, etc., I'm fine. So either one, I'll accept. Questions? Very good question. Yes, Bailey?
If the number outside of parentheses, so you have 3 parentheses, 1/2 is the x. What about if it was like 1/2 parentheses, 1/2 to x? Would that be a vertical, would that shrink?
So if you want to put, let's come up with another number, not just 1/2. Say something else. So you want, let's say 3/4 times 1/2 to the x power. Is that what you meant? No, sorry. Outside?
Yeah.
Oh, okay. So you want, instead of 3, you want a number less than 1. Yes. So you want like, let's say 1/3 and 1/2 to the x. This will be still outside of x. It doesn't touch x, it touches y. So it will be a vertical shrinking of the graph. So the graph is like this. It will be like this.
And we'll be multiplying all the y values.
All the y values by 1/3, so they will be diminished.
Okay.
So here we had multiplied by 3, that's why it went up by a factor of 3. This time all y values will be divided. Is that okay? Perfect. Okay. Do we want more transformations with this function? I want to make one up. I wasn't really impressed with the ones they showed. Okay, so base function. Very good. 2 to the x is the base function, pure exponential function. Perfect. Next is the first transformation on 2 to the x. Very good. What does this do to the graph? Excellent. Left 1. Number 2. In order of operations. Exactly. Reflect. With respect to. Excellent. See, just one simple section that we didn't really think much of at the time. It's helping us even visualize graphs without even graphing them. We can picture this now. So just one tiny section. Okay, number 3. Yes, -2 x plus 1 plus 4. Can we visualize this before we even graph it? Yes. So is this increasing on all its domain or decreasing on all its domain? Right, it's because the base is greater than 1. So you told me to shift this left 1, right? Then you told me to reflect this. And then you told me to
Lift it up 4.
we picture the graph. It's this with the horizontal asymptote, like +4. And we haven't even graphed it. Yes, I looked still in front of you with my arms up and down, but you pictured it. That's the most important thing. Good. Here's the base function. Base function always crosses at 0, 1. Always. So this is 2 to the x. Then you told me to shift it 1 to the left. This marker, this point goes here. 1 to the left. Here it is. So this is 2 to x plus 1. Then you told me to reflect this. Where does this point go? Yes, excellent, right here. So this is -2 to x plus 1. And then you told me to do what next? Indeed. But now, because this was y equals 0, the horizontal asymptote, I have to shift 1, 2, 3, 4. Y equals 4. So then, where does this point go? 1, 2, 3, 4. Excellent. Here's the graph. So just to make sure that you know that this is the final. Can anyone give us the range of this function? Excellent. Very good. Questions for me? Yes, please.
Oh,
Yes, sir.
no, sorry.
Okay. Questions? Anything? Anything? Okay. Yes, please. Mary? Yes.
So, when graphing the base function, it always goes through
0, 1.
0, 1.
Yes. If it's a base, I'm talking about base, pure exponential. If it's increasing or if it's decreasing, it will always go through 0, 1 because when x is 0, y is 1.
And then it's increasing if a bigger than 1.
Always.
It's decreasing if a is between 0 and 1.
Exactly. Like 1/2, 1/3, 1/16. Yes, it will always be decreasing. Good. Other questions here? It's always good to discuss things. It's always good to go over things and ask questions because that's how we reinforce what we learn. That is basically, in my opinion, the easiest way and the best way. Okay, so now let's continue with 6.3 log functions. Before we graph them, I would like to discuss a few things, important things with you. Can anyone give us an exponential function? Any exponential function you want.
E power x.
Say it again.
E power x.
Very good. Let's discuss that. Excellent. So let's look, before we talk about log functions, I want to discuss this. There are two special functions, special exponential functions. One is called common exponential function, and the other one is called natural exponential function. This one has base 10, and this one has base e. They are so special that the calculator has two keys designated to those two. With the second key right here, 10 to the x, in blue or in yellow, whatever, depending on your version of the calculator. And this one here with the second, right here, e to the x. Okay, common log and exponential, natural log. Okay. Now, obviously, both of them have a base that is greater than 1. Both of them will look like this. One, if we remember, we discussed this last time, 10 to the x. And the other one is slightly, not that far apart, but slightly further away from the y-axis. This one has a higher growth than this one because this one is base roughly 3 and this is 10. So 10 to the x grows as a faster rate than e to the x. So just remember these two, and of course they have special inverse functions. In a minute we'll talk about that. So we decided to work with e to the x. Okay, let's see how it works out. It would have been easier if for this particular first example we would use like 2 to the x or 3 to the x or 1/2 to the x, but let's give it a shot. I've never used e to the x for such an example. My students never picked that. Okay, that's good. Let's try. Okay, so let's pick some values. This is what is the domain of this function, by the way? Correct, it's a friendly function. Domain, all your numbers. Great job. What is the domain? What is the range of this function? Remember the graph. Picture the graph of course. Remember, picture the graph when you identify the domain and range of the base function. Perfect. So we want now to create a mechanism, of course, which is the inverse function. So let's pick some values. Let's say x equals 1, let's say x equals 0, and let's say x equals -3. When we calculate f of 1, what do we get? Y equals, this is our function, and we want to determine the y value when x is 1. Excellent. Let's see what happens when x is 0.
1.
Y equals 1. Very good. Let's see what happens when x is -3. Y equals?
Whatever.
Exactly. E to the 3rd power. Great job. So you already told me the domain and range of the exponential function. I'm going to write them one more time. So I should write so it's easier and clear. The exponential function, you already told me. The domain is a friendly function. It's defined everywhere. And the range, you already told me, is 0 to infinity. Its inverse function, which we did not name yet, we will in a minute, will be defined for sure on,
0 to infinity.
excellent, 0 to infinity, and for sure carved in stone will have what range?
-infinity.
Right, because it's going to be the inverse function. Great job.